All right, we are now recording. Let's get the slideshow set up from the current slide. I do want to go over a couple things. I think I mentioned these both on Tuesday, but nobody was here, so in case you haven't heard it yet. Several little things. Number one, first of the term, I was thinking I wasn't going to get paid an overload because even though I was teaching a lot of courses, they were very low enrollment. Not as low as this one, but, that I wasn't going to get paid. But then I was told, yes, I would be paid. So I indicated to, the overload courses, my physics and physical science, and that's under natural science, how to do math. So I indicated that, left it with the secretary so she could give it to the chair for natural sciences. Well, the chair for natural sciences never picked up the package and just turned in the contract request without faculty load things where I put the note, so she didn't see that. So now I'm right now probably not getting paid an overload, but what I did, because I was told I would be, I had already gone back in, and because if you're paid an overload, you're supposed to work extra hours because your regular load's a 40-hour week, and then the overload is in addition to that. So I had to go back into my syllabus, all 6 syllabi, and my locator card, and get that loaded into all the things. So I got those changes made, and then had to take out the old syllabi and locator cards and put in the new ones for all 6 classes. And I did that last Tuesday after this class was over with. And I think that's right. Yeah. Last Tuesday after the class was over with, I think I had said that morning that I would be doing it, that I was going to get paid. Well, I found out yesterday that they didn't submit it because she didn't see the note that I had left for her. So she didn't submit an overload for me. She said she thought I was going to do it. I said, well, I only do math. I don't do natural science. She said, oh, that's right. I do natural science. Yeah? And so I said, and that's what I indicated on there. So I don't know if she's going to remember to do it or not. But I'm going to leave my office hours like they are. What it did was extend. I was leaving at 3:30 on Tuesday, Thursday. I'm now leaving at 5:15. And most Tuesdays and Thursdays I've been here after 5:15. Today, I cannot. The other reason I was a little late this morning, I had to drop something off at a business this morning. They didn't open until 7. I got there shortly after 7, but they were so incredibly slow. They were having a lot of business because a lot of other people got there right at starting time, and one person behind the desk she's always slow, and she was very, very slow. And then I got to be back before 6 o'clock tonight to pick up. And so I have to leave here by 5:15 during rush hour to make sure I get there by 6. So there's that. Now, the other thing I found out yesterday, for sure, I had heard rumor of it. I think I told you early in the term that there was a 2-day meeting coming up. At the end of last term, I believe it was, I got an email from someone at National Science Foundation saying that they wanted teams from various 2-year schools to go and participate in a training thing they had. And it sounded like something that would benefit the college. So and they had 3 different venues and days and times. So I forwarded that to my chain of command, the associate dean, the dean, and the vice president for academics, and said, I would like to participate in this, especially if we could do the one in Spelman College in Atlanta. It's a Friday, Saturday. We don't have any classes on Friday, and that's close. I can get back, be, pretty. That's what I'd like to do if we can do it those days. Well, that day or a later day, the vice president's secretary called and said he needed to talk with me. But he wasn't available then, so we played phone tag for a while. And when I finally got to talk with him, he said, thanks for responding and to his request. Well, it wasn't his request, it was National Science Foundation. He said, we'd like to do a team. However, we want to request the one in Xavier university or college, whatever, down in New Orleans. I said, well, that's a Monday and Tuesday. He said, yeah. I said, well, I have a bunch of classes on Monday and classes on Tuesday too. I'd rather do the one on Friday. He said, oh, I didn't want to mess up a weekend. So you see, instructors think of classes, administrators think of weekends. So it's a big disconnect there. So he requested that, but with the Spelman, he said we may still they may have signed us there. No, they gave us what he requested. So that's coming up later this month, and now I'm locked into it, even though I didn't want to go on those days to that place. So I'm more than likely that Tuesday, I won't be back in time for this class. So what we'll do is try to figure out a way. Maybe someday next week or the week after I go, or whenever, if we could just continue and have class then from 10 till 11:50 and just continue. I know you've got another class or something. You have what? A job. Okay. Would sometime after 3:30 in the afternoon on Tuesday, Thursday work? No. Okay. Well, I'll check with the other student. Whatever will work best with her, I'll just record it and you can pick it up. Okay. So sorry about that. I requested otherwise and was overridden. Okay, as usual. All right. Any question on anything we've done up till now? Okay. Example 5 in the text is referring back to example 4. Okay? And example 4 was investigating this differential equation. Let me get my pen set up for the dark ink, virtual ink. dy dx, and we've hit the same one several times now, x y to the 1/2. Okay? We saw in example 4 that this possesses at least two solutions whose graph pass through 0, 0. Of course, one is a trivial solution, and the other is, and if you turn back a page, you'll see it's the x to the 4th over 16, which is one we investigated earlier. So both of these pass through the origin. Okay? Now, that's the only point they have in common, but they both pass through the origin. All right. Perfect attendance today after 0 attendance on Tuesday. Okay. I was here all by myself and talked to myself, so that's all right. It went all right, I think. I was telling Marcus before you came in a couple of things. I did go out and change some things. I was told last week that I would be paid an overload for the 4 extra classes I'm teaching this summer. 1 overload for 4 extra classes because they're small, not as small as this one, but I've got some small classes. So I had to go and change because if you do an overload, you're supposed to stay extra hours. So I had to change my office hours on every syllabus, all 6 syllabi, and my locator card, and then had to replace those in all 6 courses on the blackboard. So I did that Tuesday based on what I had been told. So now my office hours on Tuesday, Thursday used to end at 3:30. Now, my day ended at 3:30. Now I go to 5:15. Most days I'm here after 5:15, but not today. I've got to be in Homewood before 6 o'clock, so I've got to leave here right around 5:15, which rush hour traffic to make sure I get there by 6. But that has changed. And then I found out yesterday that no one submitted the contract request for me, even though I'd requested it, but the woman who was doing it didn't see the papers that she was supposed to turn in with the contract request, so she didn't do it. Hopefully she's going to do it now. I don't know. But anyway, I'm going to leave them alone. The other thing is coming up later this month. I can't remember exactly which Monday and Tuesday it is. We have a meeting down in New Orleans. Now, I had gotten an email from National Science Foundation saying, asking the college to consider sending a team because it was training for something, and it looked like something good that I thought would be beneficial. And they had one of the three options we had was Spelman College over in Atlanta on a Friday, Saturday. I said, perfect. We don't have any Friday classes, and it'll be easy to get back Saturday, no sweat. So I forwarded that on up the chain of command because they wanted a team. I couldn't just respond to it. I said they're looking for a team. If we're going to do one, I would enjoy doing it. Wouldn't mind being on that. So I finally got word back from the vice president, who was in on that email that I sent up, thanking me for responding to his email, which it was National Science Foundation, so I hadn't even seen his email. But I guess he sent it after I did and then thought I was responding to that. But he said, yes, I'd like for you to go, but we're requesting Xavier in New Orleans on a Monday and Tuesday. I said, well, that's a Monday and Tuesday. I have classes Monday and Tuesday. Oh, well, I didn't want to mess up a weekend. So, you see, instructors worry about classes, administrators worry about weekends. So, now I found out yesterday it is, we got sent to Xavier. So, there will be a Tuesday I will miss later this month. I was asking Marcus, and he couldn't do either time. The only times I have free to make up the class would be from 10 till 11:50, just continue the class right after this one on Tuesday or Thursday, or after 3:30 on either Tuesday or Thursday, 3:30 to 5:20 or something like that. Would either of those work for you? Right. And Marcus always does so. But if there's a Tuesday or Thursday coming up and you don't, either after this class or at 3:30, let me know and we'll plan to do that. Otherwise, I'll just record like I did last Tuesday. Just talk to myself, for an hour and 50 minutes. Okay. Now, we were just starting example 5 on page 18. This is where I left off last time. And we were just talking about this differential equation that we've hit, like 2 or 3 other examples so far, including example 4. And this one, example 4, showed it possessed 2 solutions whose graphs pass through the origin. And you can turn back one page if you got your book, and you'll see those graphs. Okay? And we talked about those graphs in an earlier problem, or those solutions in an earlier problem. Now, we're on page 18. Those graphs are on page 17. Okay? Now, inspection of 2 functions, okay? And this, not the same function, well, bizarre. They name a function, f of x, y, which, by the way, is your solution of this, is what your first derivative is, equal to x, y to the 1/2, okay? That's just what your first derivative is. Let's name that as a function. Now, for some reason, they have opted to take the partial, and y'all have had partials, right? Partial derivative. The partial of f with respect to y. And what is that? Say again? A little louder. Okay. It's x over 2y to the 1/2. Okay? Either he did it real good in his head or he read it from the book. Okay? Whichever. Okay. That's what the first derivative is. Partial derivative of f with respect to y. Now, the derivative function is continuous in the upper half plane defined by y is greater than 0. Okay? Certainly is, because it's continuous everywhere there. Not continuous, the f function is continuous at 0. Okay? No. It is continuous at, no, let me take that back. It is defined at 0, but not continuous there, because just to the left of that, y is negative. And you can't take the square root of a negative number. So this is the function f of xy is continuous for all y's greater than 0. Continuous for it, okay? Now, when you look at its derivative, again, that's defined and continuous for all y's greater than 0. Well, you can't have anything less than 0 there because it wouldn't work there either. Okay, so these are continuous in the upper half plane, meaning y's greater than 0. Hence, the theorem that we just did at the bottom of page 17 guarantees uniqueness and existence, okay, of a solution, okay. So that enables us to conclude that any point x0, y0, as long as the y0 is greater than 0, in the upper half plane, there is some interval centered at that x0 on which the given differential equation has a unique solution. Now, go back up and look. 0, 0 is not in that interval because that's the endpoint. It's not inside an interval, it's the boundary of the interval, okay? So that means that for every y greater than 0, that means every x, let's see, does that mean every x? No, x could be anywhere, right or left, then that would be fine. But not 0, okay? Thus, for the example, even without solving it, we know there exists some interval centered at 2 on which the initial value problem has a unique solution. Now, not just this, now they're introducing this, and y is equal to, now I'm going to say y of 2. Now, they picked some value for it, and they said just 1. Okay, that's your initial condition for that one. Now, there's no way to tell there's any problem with that. When x is equal to 2, y is equal to 1, dy dx would be a slope of 2 because square root of 1 is 1, 2 times 1 is 2. So the derivative, or the slope, would be plus 2. That's what we just evaluated there. The partial of that would be 2 over 2, because square root of 1 is 1. So that would be 1. The partial of f with respect to y would be 1. And that was the second half of the given before the theorem that the partial of f with respect to y is also continuous, and it is, as long as you don't include y equals 0. Okay. So in example 1, theorem 2.1, the one we're just looking at, it guarantees there are no other solutions other than that. Okay, I'm sorry. This is going back. This is a different problem. This is the one y prime is equal to y. Okay? Now we already, and they give us an initial condition, y of 0 is equal to 3. And we did this one recently too. That was example 1. Yeah, and that's what they said here. Okay? In example 1, that's a unique solution because all the conditions are met. The function, its derivative, partial with respect to y, everything are continuous. If you do the same one, but give initial condition y of 1 equal negative 2, okay, guess what? the same solution you had for the other one won't work. This one, it's y is equal to 3e to the x. You see, that works for that one. For this one, it would be y is equal to negative 2. And we did this too, negative 2 e to the x minus 1. Okay, we did that last time. I did it last time. Okay, so that's the one and only solution for that one as well. This follows from the fact that f of xy equal y and the partial of that equal 1 are continuous throughout the xy plane. Further shown that the interval I on which each solution is defined for this one is all real numbers. For that one, only y is greater than 1. Only y is greater than 1 because it's not defined otherwise. So, they talk a little bit more about interval of existence and uniqueness, and I don't see any reason to beat this dead horse any further. And then they have the remarks, which are usually sort of esoteric, sometimes pretty practical. The one thing here, though, under the third remark, Roman numeral 3I on page 19, says initial conditions are prescribed at a single point, x0. But we also are interested sometimes in solving differential equations that are subject to conditions that specify y of x or its derivative at two different points, x0 and x1. When you do that, we usually call those boundary values, okay? Conditions such as, they're not even giving us the formula. If you have y of 1 is equal to 0 and y of 5 is equal to 0, okay? Those could be boundary conditions. One's at point x equal 1, one's at x equal 5. That would give you, say, a boundary. That could be a vibrating string that's fixed on the two ends at 0 and 5, at 1 and 5, and you know they've got to be 0 there, and then what's happening in between. That's one possibility. That's not the only. Or let's say we have y of pi halves is equal to 0, and y of pi, or y prime of pi, you could have the derivative defined, and that's equal to 1, okay? Well, if that's the case, one of these is a pi half, one is a pi. Those are boundary values. Do these work as well as condition? That's a boundary value problem. These are initial value problems. If you have more than one, they're all at the same value for x. Boundary value, you could have more than one, but they're at different values for x. And they can be either the function itself or it's a derivative. Now, they suggest you see some problems. When we start to solve the differential equation in chapter 2, we will solve only first order equations and first order initial value problems. The mathematical descriptions of many problems in science and engineering involve second order initial value problems or 2-point boundary value problems. We'll examine those in chapters 4 and 5, so why spend all this effort? But in case you run into that, this is different from that because that's an initial value. Of course, those are first order, so you can't tell the difference. These are second order, and these are boundary values rather than initial values. So homework exercises, do number 1, then either 3 or 5, or both, either 5 or 7 or 9, or both, either 11 or 13, or both. Do 15, any of the odds 17 to 23, either 25 or 27, and then any of the odds 29 through, goodness gracious, 37. No, I'm sorry, 33. 29 through 33. Then do some of the odds, either 35 or 37, you choose, and then do any of the odds 39 to 43. The discussion problems, nice to look at and think through, but generally they don't have answers in the back. The other odd ones do, that's why I assigned them. Okay, any questions? Let's move on to 1.3. Now, I think I may have said this before. I may have said it last Tuesday when none of you were here. Neither of you were here. So let me say it again now, just to reiterate. When I first started teaching the course from this text, I've taught it a few times from other texts, didn't like them. I don't really care for this text. It's great, but it's so much better than the others. Okay, so best I've found so far. The one I had when I was in college myself, a sophomore in college, was a fantastic text. I thought differential equations made so much sense. You know, it just laid it out perfectly. I had to turn in the text because I was on a Navy ROTC scholarship, and they provide books, but we had to turn them in at the end of the term. So I didn't get to keep it. I wish I had bought it. Okay, I didn't have the money to back then, but I wish I had, because it was a fantastic text. I'm sure the author's dead, you know, and it's not being printed anymore. And they just had a different way of presenting it back then. But anyway, once I started teaching for this, basically chapter 1 is not required by the course description. But I found out if I started in chapter 2, no one knew the nomenclature. So I had to do something in chapter 1. So I decided I would just combine chapters 1 and 2. And then it was so late into the term before we ever could finish the first, that 1 and 2 together. It took a long time to get to the first test, and people were antsy about how I'm doing. So I decided to split off and do one short test after chapter 1, which is coming up fairly soon. And then chapter 2 is a big, long chapter, covers a lot of material, and then do a separate test on it. And I just thought chapter 2 is going to be the hard test, chapter 1, just a nice, easy test. Ever since I did that, people really foul up test 1 way worse than they do test 2. And the only thing I can figure is they're not doing the homework. Now, it's not you. You may be. But the previous classes, I could not see why they were messing up chapter 1, because it's really pretty straightforward stuff. So, but the problem is you're not really solving anything. You're showing this as a solution, which to me I think is easier. But when it comes to test time, they just weren't doing it, So please do those homework exercises. That's why I give them. That'll make the test make more sense when I give it to you. Okay. That was my commercial. Let's get on back to the programming. Okay. 1.3, differential equations as mathematical models. Now, we're not going to go huge detail here. Mathematical models are often desirable to describe the behavior of some real-life system or phenomena, whether physical, sociological, economic, whatever, in mathematical terms. And guess what, team? If they have changes in that term, rate of change, if you see that, that's a derivative. Something changes with respect to something else, that's a derivative. If change is involved in your model, you've got differential equation. Have to happen, okay? So the mathematical description of a system of phenomena is called a mathematical model, constructed with certain goals in mind, blah, blah, blah. Construction of a mathematical model of a system starts with identification of the variables that are responsible for changing the system. Notice the word changing. Change, if there's change in there, is differential. It's a differential equation. But you got to identify the variables. Now, what's more, you always have at least 2 variables, right? If you only have 2, one's independent and one's dependent. You have to identify which is which. They're not always X, Y, okay? They could be consumption of fuel, hours that the equipment operated, okay? Which depends on what? The consumption depends on how long you run the equipment, whether it's a car, a truck, or lawnmower, or whatever. The consumption depends on the time. Well, that's so anyway, you identify the variables. that are responsible for changing the system, we may first choose not to incorporate all the variables into the model at first. This step, we're specifying the level of resolution of the model. Next, we make a set of reasonable assumptions or hypotheses about the system you're trying to describe. Those assumptions will include any empirical laws that apply to the system. Like if you're talking about an area, you might have to include the area formula there. Okay? If you're talking about, a volume, you might have to do that. Okay? Since the assumptions made about a system frequently involve a rate of change of one or more of the variables, the mathematical depiction of that is a derivative. That's what I was saying earlier. Once you've formulated the mathematical model that is either a differential equation or a system of differential equations, you're then faced with the not insignificant problem of trying to solve it. Okay? Now they have a little algorithm, I guess, at the bottom of the page. The trouble is you can't tell where to start this. Okay? Let's start in the upper left. What are your assumptions and hypotheses that you're dealing with here? Okay? You have to know your system, identify those. Express those assumptions in terms of differential equations, if you involve that. That gives you a mathematical formulation. Solve the differential equation, not the most trivial of steps. Okay? That gives you solutions. Maybe not all the solutions, a bunch of solutions, but you may not know which one. Display the predictions of the model as in graphically. What are you expecting the solution to look like? How does your solution fit in with what your expectations are? Check the model predictions with the known facts. If they don't line up, change your prediction or change your model. Okay? If necessary, alter the assumptions or increase resolution of the model. In other words, you might bring in other variables that might be pertinent. Now that's kind of an idealistic system, and that's sort of a straightforward approach. A lot of times in medical and other things like this, you start out introducing as many variables as you can think of that might have some pertinence there. Throw them all into the model. Then start running some early analysis statistically and see if any of these have no significance. If they are, then you weed those out. So this is sort of an analytical approach. The other is an empirical approach. An analytical approach, you usually start simple and then modify by introducing additional ones. Empirically, you start with the whole passel and then eliminate those that your analysis shows are not really significant. Okay? A mathematical model of a physical system will often involve a variable time t. A solution of the model then gives a state of the system that is true at various times t. That's what you're coming up with. So let's take a look at population dynamics. One of the earliest attempts to model human population growth by means of mathematics was an English clergyman, but also an economist, Thomas Malthus. Okay. Now that may or may not seem unusual to you. Here you have a clergyman who's an economist. Well, if you think back to those times, sometimes your most educated people were the people from the church because, frankly, the church ran the education system through the Dark Ages. That's the only place literacy occurred. So it wasn't at all surprising that clergymen were sometimes the best trained, they had the most education. So he was a clergyman, but also was interested in economics. So Thomas Malthus, pretty famous name in economics. Okay, this is 1798, so it's well after the Dark Ages. This was in the after the Renaissance even, but still that persisted. Basically, the idea behind Malthusian model is that the assumption that the rate at which the population of a country grows at a certain time is proportional to, okay? Now, they have a little footnote on what that means. And I will do it in terms of that. The rate, okay, the rate at which a population of a country grows at a certain time is proportional to the total population of the country at that time. Okay? Now, what are we dealing with? Population, time. So the rate of population growth would be dp dt. How is the population changing with respect to time? And his assumption was it's proportional to. Now that little symbol, or something like that, mine's pretty ugly, that means is proportional to. Okay? The rate of population growth is proportional to the population itself. Okay? That almost seems circular logic. But if you think about it, it's really true. If you have a very low population country, then there's fewer people to get married, fewer people to have kids, and guess what? The rate of growth is pretty slow. But if you have a huge country and lots of them are getting married and stuff and having kids, then the population is going to expand more rapidly, or has potential to. So this was the first of his things. Now, no one had even thought in these terms before. Okay. So in other words, the more people there are at time t, the more that are going to be in the future. Okay? So that would be how we would express that concept. Now, you're probably not used to dealing with proportion. Okay? How do you change that proportion to an equation? It's pretty simple. dp dt is equal to k times p. So to go from proportional to, just make it equal k. Proportional to means equal k, okay? Just think of it that way, where k is some constant proportionality. Now that constant proportionality shouldn't be dependent on time. That should be something that's not dependent on time. That may be dependent on customs. It may be dependent on GDP, you know, how much money, it could be dependent on other things, but it shouldn't be dependent on time. Could be dependent on health, specifically prenatal, perinatal health. In other words, how much assistance do women get when they're giving birth? Do they get good care before they deliver children? And do they get, is the delivery process pretty safe? And in other words, do you not have very much infant mortality? So those things would influence the K. Now, later you might say, hey, you know, we need to put that into the model. Not just have two variables, but have a third variable, or a fourth variable, or a fifth variable. We're going to start with this one. That's what Malthus did. Okay? K is a constant proportionality. In this simple model, which fails to take into account many factors that can influence human population to either grow or decline, immigration, that doesn't enter the picture here at all. Okay? So you probably will need a term for that. Now that could be, these two words sound alike, but they're quite different. IMM is people coming into the country. Think of I into. EMI is people leaving the country, right? Immigration, you immigrate to another country, that's EM. You immigrate into a country, that's IM, okay? Exit, E, enter, not enter, into is I, okay? Ireland, during the potato famine, are y'all familiar with that? Back in the 30s or 40s, somewhere around in there, Ireland suffered enormously from a complete, I think, multi-year failure of their potato crop. And that was the main staple for populations there. So lots of people died, and I think lots more people left. That's when the big Irish immigration into the U.S. came. So when you see names like Giuliani, you know, very Irish sounding name. No, I'm sorry, that's Italian, sorry. The O'Kellys, O'Reillys, you know, all these kind of things, lots of them came over in the 1840s. Actually, the Fowlers, I think, were British who were living in Ireland. They suffered too. They came over around the 1840s and 50s, around the potato famine. Guess what? Ireland's population today has still not made it back up to where it was before the potato famine. So yeah, immigration, exiting, can make a big, big difference, as well as mortality and stuff. Okay. Nevertheless, this model, even though we've had a lot of immigration, not much leaving, but mostly coming, it still has predicted population in the U.S. from 1790 to 1860. Okay? Populations that grow at a rate described in 1 by itself, this formula here, very rare, but nevertheless are still used to model growth in small populations over short periods of time. For instance, you may not be talking about people at all. Bacteria in a petri dish. Deer in the wild, you know. Rabbits in the wild. That would be a big case for that. Okay. You know, various things such as that. Or even domesticated, say rhinoceroses in captivity. You could do just lots of things as long as it's small populations over short periods. Now, another, radioactive decay. Are y'all familiar with this? The nucleus of an atom, most atoms, usually pretty stable. That's good. Okay. However, some of the big, monstrous atoms, such as uranium, plutonium, radium, radon, some of these really big, cesium and americium, some of those really big, bulky nuclei, they're not stable. Okay? They either don't quite have enough neutrons to create stability, or they have too many neutrons. Okay? So in other words, some isotopes of those that I named are radioactive. Others may be fairly stable. But because it's such a big, bulky nucleus, it's real easy not to be in perfect harmony. Okay? So you have things that radioactively decay. Okay? For example, over time, the highly radioactive radium, that's Ra-226. Now, what does that mean? I don't have a periodic table in here. There's one back in the office there, I'm sure. But radium, every radium atom ever has the same number of protons. Because they have a different number of protons, it's a different element. Okay? And that number of protons is somewhere, I think, in the 90s. Okay? Don't know for sure, maybe upper 80s. I believe it's somewhere in the lower 90s. So let's just say it's 90. I don't know if it is. I could check. But let's say it is. Well, that means this 226, that's the atomic mass of this particular isotope. Well, if it's 90 for the protons, that means you have 136 neutrons in that nucleus. That's a lot of neutrons, okay? So if that's either 1 or 2 or 3, several too many or too few, you've got an unstable situation. And since this is highly radioactive, I guarantee you have an unstable situation, okay? But this highly radioactive radium transmutes or decays into radon, Rn-222. Okay? Now, how does that happen? Well, notice there is a loss of 4 atomic masses, right? Now, what happens, what kind of radiation has an atomic mass of 4? Alpha radiation. Alpha radiation is the basically the nucleus of a helium atom. Okay, 2 protons, 2 neutrons. That would do it. And whatever radium is, radon is 2 less on the periodic table, meaning it lost 2 protons, but it also lost 2 neutrons as well. Okay? Now, to model the phenomenon of radioactive decay, what we do, the rate at which it's decaying, what we have here, now they don't say this very clearly. They should really say, let A be amount of the substance you started with. Okay? Yeah, they do say it, but after they've used it a couple of times. So A of T is the amount of the substance. This will be the radium. Okay? And because it's radioactive decaying, that amount is always changing. Okay? So, since it's changing, and by the way, it follows the same as population model. The rate of change of radium with respect to time is proportional to the amount that you have. Okay? The more you have, the more it decays. Now, let me give you a really lousy example of that. Nuclear power. Nuclear power, I don't know for sure what these power plants use, but I do know the first 2 atomic bombs that were dropped in Hiroshima and Nagasaki, one was uranium-based and the other was plutonium-based. Both of those are radioactive, unstable radioactive nuclei, is what they used. Now, you can have that uranium sitting around or that plutonium sitting around. You're not going to blow anything up. You're not going to have a nuclear explosion. You're not going to have even controlled nuclear, okay? Until you get what they call a critical mass. And when you reach that critical mass, then all things break loose, okay? And what's happening there? You have neutrons that are sort of floating around interacting with nuclei, and usually it doesn't cause any problem. But when you get the critical mass, now you have enough neutrons messing around to make these unstable. And then you have explosions. Or you have the power in a submarine or an aircraft carrier or something else, or a power plant, that's controlled. The hydrogen bomb. So, how did they make the hydrogen bomb? I mean, not hydrogen bombs, the atomic bombs. They had 2 hemispheres, each having less than that critical mass. As long as they had those, no problem. But they had them within the same region, but then they had explosives outside of them. So what happened, when they dropped those bombs, they were on their way down. If they had just fallen onto the ground, then they'd just made a big hole, and that's all. No nuclear explosion. But what happened, they had it timed so, I don't know how they did this, either timer or a sensor, when they got a certain distance from the ground, then the explosives, the conventional explosives, TNT or whatever, that they had in those bombs, they ignited, okay? Long before it hit the ground. Not long, but before they hit the ground. They ignited and forced those 2 hemispheres together, creating suddenly a critical mass. And when that critical mass was created, boom, there was the atomic bomb. They wanted that to happen above ground to create the maximum effect. So that timing of that, it had to happen, and there was a short delay after the critical mass is hit until the chain reaction began and they actually blew up. So this is what this means. The rate at which those changing the amount of that substance is proportional to how much of the substance you have. If you have that critical mass So there's your example of that. How do you make that proportionality into an equation? dA dt is equal to sum k times a. Proportional goes to equal k. Books never say that, but that's what I found is always true. Okay? Here's another one. And again, they do a lousy job identifying the variables. In fact, I don't even see it. Oh yeah, there it is. Let's say you have so much money. Let's call that S equal the amount of capital. Okay? The amount of capital, in other words, money that you have. Okay? Now, the ds dt, the rate at which that is changing, you could go through the proportionality and stuff, but that's equal to, and this time they're going to use a different thing, RS. You can call it K, you could call it R, or whatever. That would be if the annual rate of interest, R, is compounded continuously. Okay? That would represent that. Now, today that rate is really, really, really small. Most of the time, 1% or less. I think my checking account is 0.25% and my savings account is 0.5. I don't store a lot of money in either one of them. I'm just not getting anything. So that's a really small amount. But maybe mutual funds or possibly speculation or something else, you might get a much larger rate. Well, if you just got a little bit of money to put into it, let's say $100 and the rate is 1%, you're going to make $1, okay, in say a year, or you'll make a little more than that, but it's going to be pretty paltry. But if you have $1 million that you put into that at 1%, that's going to be, you'll make $10,000 in that year. You know, that's not too bad. You know, I could handle $1. I can't even buy a cup, well, maybe a cup of coffee, but not much more. But $10,000, I could buy quite a bit of stuff for $10,000. So you see, the rate at which things depends on, even if this is a fixed thing here, it depends on how much you got. Okay. A single differential equation can serve as a mathematical model for many different phenomena. Look at this one. Population of bacteria, of whatever, radioactive decay, savings, or, now this is even worse, what if this is your debt? The S is the amount you have of capital that you owe. If that's just a small amount, the odds are you can probably pay it off before you have to pay too much interest. But if that's a huge amount and your business isn't doing well, then the debt is piling up faster than you can pay it off. So you're only, in fact, that happened to a neighbor of ours. My home in Georgia, where I grew up, we had neighbors, the farm right next to ours, were dairying. Now, dairying is a more expensive process than regular farming like we did, but it had a lot greater return, too. I mean, milk sold for pretty good prices. But it just got to be that family's mentality is always to borrow as much as they could to keep their equipment as new as possible and have things as fancy and as good and as nice as it could be so they could keep expanding the herd and expanding things. Well, guess what? Just one little down year, or prices fell for milk or something like that happened, and all of a sudden they had so much debt that they couldn't keep up payments. In fact, that's where his original goal is just pay off the interest every year. And very seldom hit the principal. Well, after a while, they couldn't make the interest, and then And it took them a while, but after a while they declared bankruptcy, and the dairy is no longer a dairy. Okay. In fact, my family bought some of the land to help them out, get out of the bad shape they were in. Okay. Now, by the way, this is usually population growth, so the K could be positive. This is radioactive decay, so this K could be negative. But the model still works for either one. This is usually growth there too. So you see, by changing your K, you can change the rate at which things are happening. Okay? Sometimes it's decay and sometimes it's growth. All right. Here's a very different kind of an example. And sometimes I'm pretty sure I'm spending way too much time on this for what it's worth. Newton's law of cooling or warming, it goes for either one of them. According to Newton, boy, this Isaac Newton, man, he came up with 3 laws of motion. He came up with a theory of gravitation that had never existed before. He came up with study of optics that had never happened before. He came up with a whole new mathematics, calculus, okay, from which differential equation comes. In fact, he probably dealt with differential equations. He came up with rules for heating and cooling. He came up with, there's seldom been an individual that had more impact, wider impact, a deeper impact than that one individual did. I mean, incredible. Interesting character himself too, but not the nicest person to be around from what I've read about him. Okay, but he was incredible. Okay. According to Newton's empirical law of cooling and warming, oh, and by the way, he came up with ways to solve find roots of equations. Nobody has gotten any better than his. He came up with the best method. It didn't take years. Oh, well, we can tweak this, we can tweak that. No, he came up with the best model to begin with, and no one's beaten it yet. Okay, I don't think anyway. Okay, but he says that the rate at which the temperature of a body changes is proportional to the difference between the temperatures of the body and the temperature of the surrounding medium. Yeah, you know that's true, don't you? If you, and this doesn't mean a human body, okay, but I'm going to give the example of this. If you are outside right now when the temperature is pretty nice, you're probably going to stay fine, okay? But if it jumped up to 120 out there, your body temperature is going to respond because the environment is just so much warmer, you're having a harder time maintaining your equilibrium. If it got suddenly down to 20 degrees Fahrenheit, you have a hard time making that because your body can't keep up. So the rate at which, and this is more talking about, the Thanksgiving turkey, okay? The rate at which it is going to cook, the temperature change in it depends on the temperature of the oven and its temperature, okay? So lots of things follow this kind of thing. The so-called ambient temperature, the surrounding medium. If T of T represents the temperature of the body at any time T, and T sub M is the temperature of the surrounding medium, then the rate at which the temperature of the body changes, d capital T, d little t. Now this is a little strange, dt, dt. Capital T is temperature, little t is time. Okay? The rate at which the temperature of the body changes, then Newton's law of cooling warming translates into this is proportional to the difference in temperature of the body, that's T, and the surrounding medium. Now, generally, the surrounding medium is a fixed temperature, so that's a constant. Okay? So you change that to an equation by dt, d little t, is equal to some constant k, and they use k again, the difference, t minus Tm. Now, I have trouble writing Tm because a lot of times in physics you call that T0. Okay, but they're calling it Tm. So there's another differential equation. It looks somewhat similar to the others, but it's different in that it's not proportional to the temperature itself, but the difference in temperature. And guess what? As this temperature gets closer and closer to this one, the rate of change is even less, right? It drops off dramatically. So since the rate changes, then it's slower getting to that temperature. So it's very slow going there. I know that think of a decent example here. The other night, my wife fixed a really good chicken dish. We liked it. She's fixed it many times before. Really good. Pulled it out of the oven, and it was really, really hot. Surrounding temperature in the house was pleasant, 70 degrees, say. For a while, you had to use a hot pad only, and she had fixed rice stew. You put the chicken over rice. Great. Okay. I came in late that night. I think it was Monday night, maybe, when I teach late. And came in late. And she had had it out of the oven for hours at that time. But it was still pretty warm. Now, when she first came out of the oven, really, really hot. But because there was a big difference in temperature between the air and it cooled pretty quickly to begin with. And then got to be warm just a little bit more than that. So still, I didn't need to put it in the microwave. It was still warm enough, so I got my rice and put the chicken on it, and it was really good. And then later, that night, maybe sometime later, I went to put it in the fridge because we were going to keep it in the fridge overnight, and it hadn't gotten that much cooler. It had dropped off in temperature really quickly to begin with because it was so hot. Ambient temperature was much less, so it went by this rate. But as these temperatures got closer together, the rate at which it fell was much slower, so it only dropped another degree or two in that next hour, where it had dropped probably 15 or 20 degrees, more than that, 100 degrees in the first probably a few minutes. And this hour that from the time I ate it till I went to bed, it only dropped maybe a degree or two. It was still warm. Not as warm as it had been, but very slowly changing temperature. Okay. Dumb example, but there. Okay. Spread of a disease. Contagious diseases like the flu virus, Ebola, Zika, these things, they follow a rate. Now let's see, in this case we assume, okay, let X of T denote the number of people who have contracted the disease. Okay, that could be flu or whatever. Okay. Y of T, the number of people who have not yet been exposed. Okay. Seems reasonable to assume that the rate dx of dt, the rate at which people are contracting the disease, is proportional to the number of encounters or interactions. It's proportional to the number of encounters or interactions, okay, between the two groups of people. So that'd be proportional to the product or some product X and Y, interactions between the two groups. If the people with the disease only associate with people with the disease, in other words, they've been quarantined or isolated, the disease is not going to spread. But if people with the disease interact with people without the disease, then it's going to spread. And if people with the disease don't interact with anybody, really quarantine, people without the disease, they're not in contact with them, so it's not, yeah, okay. So it's proportional to the interaction there. Now we put multiplication, it could be x to the 1/3 and y to the 2/3 or something like that. It doesn't have to be this, but we'll just leave that. Change that to a equation, differential equation, dx dt is equal to k times xy. Okay? Now, where k is the usual constant of proportionality. Now, suppose a small community has a fixed population of n people. In other words, it's not something that's going to spread outside, so the number of people that could get it is rapidly increasing. Very small population, it's isolated and only has a certain number. So if one infected person is introduced into that community, it could then be argued that x of t and y of t are related by x plus y is equal to n plus 1. Okay? In other words, the total number that have the disease and those that don't have the disease is the number of people in the original population plus that one who initially came in with the disease. Okay? Because once he's interacted with others, it happens. So then what we do is solve this for y. So y is equal to n plus 1 minus x. All right? Yeah. Then our equation becomes dx dt is equal to k times x times n plus 1 minus x. Rather strange looking form, but there it is. There is a differential equation, and said with this particular problem that we just did, the obvious initial condition would be then the x of 0, the number of people affected at time t equals 0, because t is the independent variable, would be 1. That's that one person who came in with the disease. So there you have a complete equation, and you can deal with that. Okay. Chemical reactions. Start with a clean page here. Again, I'm probably taking way too long with this, but just illustrating how many uses you have of this. The disintegration of radioactive substance, now we go back to that again, governed by a differential equation, we say is a first-order reaction. In chemistry, few reactions follow the same empirical law. If molecules of a substrate A decompose into smaller molecules, now this isn't radioactive decomposition, they're changing the chemical composition. It is natural to assumption that the rate at which the decomposition takes place is proportional to the amount of the first substance that has not undergone conversion. That is, if x of t is the amount of substance A remaining at any time t, x of t amount of substance A remaining at any time t. Okay? So that's why the t is in there. That's a capital X, by the way. Okay? Then dx of t, dx dt is going to be, just like we've seen before, k times x, proportional to how much of x is still in that form. Now, here k is a negative constant, just like it was with radioactive decay. Okay, since x is decreasing. Oh boy. Didn't know we were going to get into some chemical formulas, but here we go. This is T-butyl chloride, CH3, that's a methane group, 3 of those around a carbon and a chlorine. Okay, I can almost picture that. Carbon's in the middle. You have 4 combination sites around it, because carbon has 4 unpaired electrons. 3 of those are occupied by methane groups and 1 by chlorine. Okay, so think of the chlorine on top and the base is the methane groups. Okay, that's going to react with sodium hydroxide, a very strong base, sodium hydroxide. Okay, now usually it's a 2-way reaction, but they're just showing it 1, so I'll just do it as 1. And that produces CH3, 3 still, COH. In other words, the chlorine ion here has been replaced by the hydroxyl ion here. That gives you, it's a type of alcohol, what is it? T-butyl alcohol, okay, same type name, okay? Plus, what's left over? NaCl. And we know what that is. Salt, table salt, okay? I wouldn't use it because it's mixed up in your T-butyl alcohol, okay? Or maybe you would, I don't know, okay. Now, only the concentration of T-butyl chloride, that first thing, controls the rate of the reactions. But in the reaction, and they draw it, oh. Okay, here's a different reaction. CH3Cl, boy, that's strange. Now the CH3 is acting like a cation, which is strange, plus NaOH, sodium hydroxide, a pretty strong base. It produces CH3OH plus NaCl. Okay. One molecule of sodium hydroxide, so NaOH, is consumed for every molecule of methyl chloride. That's what that's called, methyl chloride. Thus forming 1 molecule of methyl alcohol, okay, and 1 molecule of sodium chloride, NaCl. In that case, the rate at which the reaction proceeds is proportional to the product of the remaining concentrations, methyl chloride and sodium hydroxide. So this one depends only on this concentration. This one depends on the product of these two. So you see you have 2 different rates of reaction there. So, and because they're tied together, and I'm not going to get into all the thing, if A is decreasing and B is increasing, or vice versa, then you have different reactions. I'll just write down the thing. dx dt is equal to some constant of proportionality, alpha minus x times beta minus x. Okay, where alpha would be one substrate and beta the other. So you see you have a much more complicated system than this one right up there. Okay. All right. I don't know if you remember back in math classes, they used to give you the mixture problems. Remember those? And as long as everything was mixing regularly, you could do them, you know, just using mathematics. But if you're trying to get at a fixed point in time, then lots of things could be changing. And here would be a typical situation. Now, A here is amount of salt in pounds in a tank. So A is amount of salt in a tank. Now, it's not just a pile of salt there. It's mixed in water or some other liquid. Okay? Now, let's say that you have Suppose a large mixing tank initially holds 300 gallons of brine, that is water in which a certain number of pounds of salt has been dissolved. Another brine solution is pumped into the large tank at the rate of 3 gallons per minute, and the concentration of the salt in this inflow is 2 pounds per gallon, whereas the original, it was, I thought I just read it, but I don't see it now. Oh, it just said a certain number of pounds, okay? When the solution is well stirred, it's pumped out at the same rate as the entering solution, and then what is the amount of salt at any time t that's still in the tank? Well, this is a little complicated, but dA dt, the amount at which you're changing the amount of salt in there, is equal to the input rate of salt this makes perfect sense, minus the output rate of salt. Of course, that would be how much salt you have in the system at any time t. So this would be some Rn minus R out, where R is the amount of salt in the tank that's coming in, rate at which is coming in, minus the rate at which it's leaving. The trouble is, those are, sometimes you don't know exactly what it is, okay? Well, the rate in is 2 pounds per gallon. That was the concentration of the salt water that's coming in, and it's coming in at a rate of 3 gallons per minute, okay? So you see you got 6 pounds of salt coming in per minute, okay? So this is 6 pounds per minute, okay? The R out, this is R in, they gave you that in the problem. The R out is, now here's the trouble. We don't know how much salt is in there, but we do know it's A of T. That's how much salt is in the tub at any time T. And that's in a 300-gallon tank, okay? So this would be in pounds per gallon, okay? And you're pumping out at the same rate, 3 gallons per minute, because you're pumping out the same rate. So this gives you 3 times A of T, oh, I'm sorry, 0.01 A of T, okay? And that would be in pounds per minute, okay? Now they just left over 100, which I could do. Those 3 will go into 300, 100 times. Okay, we'll leave it like that, okay? So the net rate would be 6 minus A over T. So this formula up here would be 6 minus 100, well, A over 100, which then they write as 100th A, which is what I was going to do to begin with. You rearrange that and set it up as a differential equation this way. dA dt plus 1 over 100A, move that to the other side, that's equal to 6. Now the reason you write it in that form, this is sort of a standard kind of form we'll see in chapter 2 that we usually use to solve equations. Okay. So, a lot more complicated. Remember, those mixture problems always were a little complicated, but you set it up this way. Every step sort of makes sense. You just have to take them a little at a time. Yep, this is one long section. Okay, draining a tank. That almost sounds like the same type thing we were doing. And by the way, this uses Torricelli's law. So if you haven't settled on a paper topic yet, who was Torricelli? How did he develop this law? Where do we use it? I'm just going to give you the high points here. But you can read all the things in here. Here's your differential equation. dV dt, that's the rate at which the volume in the tank is changing, is equal to minus A sub h, okay? And A sub h is the area of the hole at the bottom, okay? So yeah, that how fast it's going out is how big that hole is, times the square root of 2GH. Of course, Torricelli came up with that. That basically means, and you need to look at the picture. Do you have a book? You don't? Oh, you do. Okay. H here is a height, because if you have a big column of water here, there's more pressure. And by the way, the pressure is related to GH. So the higher the column of water, the faster it's going to run out of that hole at the bottom. Whereas the lower the column of water, it's going to sort of dribble out the hole. So that depends on the square root of GH, of 2GH, okay? And it's a negative thing because it's the rate is decreasing over time. The volume, as water goes out that hole at the bottom, the rate at which it's leaving is a negative. Okay, so that's why it's a minus sign. Okay? Now, but the rate at which the height is changing, dH dt, might also be important in the problem, and that would be minus AH over AW. Now that is the amount of what was your A? I didn't write everything down. If the area, oh, that's the area of the hole. And what is the AW? Is the constant area of the upper surface of the water. Oh, I see in the picture. What difference does that make? Okay, I'm not sure. But that is, oh yeah, because you're talking about the height going down, so the area, since there's a volume leaving, since this is dealing with V, volume is height times area, assuming this is a constant thing, so then the area doesn't change, so the rate at which the height does change, and that would be times your square root of 2GH. So you see you can get two different differential equations out of this. Rate at which the volume is changing, also rate at which the height is going down. Okay, and again, it is going down because it's negative. Okay? When you're talking about series circuits, you, boy, this is getting into some physics here. So I can't teach you the physics, but here you have a series circuit in which you have an inductor, and the inductance is given in L, a resistor, whose resistance is given in R, and a capacitor, whose capacitance is given in C. Okay? The current after the switch is closed is denoted by I as a function of time, T, I of T, and the charge on the capacitor at time T is, at any time T is denoted by Q of T, charge, okay? The letters L, R, C are inductance, resistance, and capacitance. Now, Kirchhoff's second law, which is called the loop law, if you follow one loop around, the picture is there at the in the margin there, and these get to be a little, they're really pretty fun to work with, but you have to realize current is dq dt, change of charge pertaining to time. That same charge that is on the capacitor as a function of time, okay? So basically then you get to this kind of a differential equation. L, your inductance, times change of current with respect to time is equal to, and by the way, because I is equal to dq dt, then you can make this L is equal to d2q dt squared, because you substitute I dq dt, and that gives you second order differential equation there. And I don't know why I put an equal sign in there. There's no equal sign there. It's L times that. Sorry. Okay. Lost where it was. And by the way, your voltage drop across a resistor is I times R. That's good old Ohm's law. Okay. But I, of course, is dq dt, so this would be R times dq dt, okay, from this right here again. And then your capacitance, the voltage across the capacitance, is Q over C, okay? They put it 1 over C times Q. And then, so your total voltage drop as a function of time is equal to LD2 Q dt squared plus R dq dt plus 1 over C Q. Okay? That is your voltage drop at any time t is that. So now we have a second order ordinary differential equation with these coefficients, and that gives you this. Next chapter we'll learn how to solve this kind of thing. We won't probably do one that complicated, but we will do how to solve this. Okay? Guess what? We're going to bring up Isaac Newton again. Okay? Falling bodies. Now, actually, Galileo is well known for this as Isaac Newton. Isaac Newton actually refined, I would say, what Galileo had done. But Galileo did it first. To construct a mathematical model of motion of a body in a force field, one often starts with the laws of motion formulated by Isaac Newton, that he borrowed some of the concepts from Galileo, who had lived before he did. Newton's first law of motion, which basically is sometimes called Galileo's law of inertia, and then the second law, that when you have a net force, that produces acceleration. Okay? So if you combine those two together, well, Newton's second law says mass times acceleration, which is d2s dt squared, is equal to mg. That's the force due to gravity, and it's really a minus. That's the driving force on it. So you could divide out the m's and have d2s over dt squared is equal to minus g. Well, guess what? That's saying the acceleration is the acceleration due to gravity downward, minus, okay? Nothing too earth-shattering there. But then if you go about, if you know that is your differential equation, and you know an initial condition, say s of 0 is s0 and s prime of 0 is v0, then you get into the equation s of t is equal to minus 1/2 gt squared plus v0t plus some s0, whatever your initial position was. Okay? And Galileo's supposedly famous experiment, whether he actually did it or not, we don't know, but he threw a rock off the top of the Leaning Tower of Pisa. He was from Pisa, so whether he really did this, I don't know. he came up with a formula very similar to this. S sub 0 would be the initial position of the rock, which is the top of the thing, S sub 0, and then gravity is accelerating it down, so that's that first term. Your initial velocity, let's say he threw it up and down, then that would be, initial velocity would be up, but then it changes and goes down. So that would give you completely that description. Boy, to me, they should have been mentioning Galileo in that first one, but he probably also did this one too, when he, including air resistance in it. You have two competing forces. Gravity is pulling it down, but then air resistance is moving, is retarding that, is providing resistance to that motion downward. And that's called viscous damping. Your second force is minus kV because the dampening force, the viscous force, depends on the velocity through the fluid. Now, here's a dumb example I give. You probably never did this as a kid, but I remember when back when I was a kid, we didn't have air conditioning in our vehicles, any vehicle. I can't remember how old I was before we bought a car that really had air conditioning in it. It was usually roll down the window and drive 60. That's the 460, air conditioning system. Okay. But so we always had the windows open, especially in the summertime. So I like to stick my hand out the window. Well, of course, if you're going on slowly, you can feel a little resistance, but not a lot. If you're going 60 or 70 miles an hour down the highway, it would almost dislocate your shoulder. Okay? So the viscous force depends on the velocity of the medium, okay, or through the medium. So that's one equation right there. Let me see if I can find it again. Yeah, I can't find it, but it's kV. There it is, I guess, right there. Well, I can't see it, I don't know. So the total force acting is gravity downward, which is mg, minus your resistive forces, kV. Okay, that's the resistive force up. Strangely enough, they've got down being positive here, but that's okay. Okay? But if we think about what acceleration is change of velocity with respect to time. So ma is equal to, that's your net force, is equal to mg minus kv, but getting a in terms of v, that's m times dv dt, that's what acceleration is, equal to mg minus kv. Okay. Now, if you want that in terms of displacement, this is m2, the second derivative of displacement with respect to time, because time squared, because velocity is ds dt. And if you get that on the same side, then make this plus k ds dt, and then on the other side is mg. There's your force downward. Okay. All right. Suspended cables. By the way, these are called catenaries. It's the shape of that. And it's a fairly complicated looking setup that you have here with tensile forces and various things like this. But your differential equation comes out being dy dx is equal to tan theta. This is what it boils down to. But the tangent of theta is related to the weight that's on that divided by T1. Now, usually T1, that's your tensile. Okay. Okay. Now, Have you ever noticed that power lines sag between the poles? Of course they do. Have you ever thought, well, shouldn't they put more tension in them? Because if you wouldn't need as much cable. You could just have straight here rather than this length here. You'd save on length, right? Well, guess what? Because that cable has a finite weight, it's got to have gravity acting on it, so it's always going to sag a little bit. Okay? Now, let's say that it was the middle of the hottest summer day of the year. Those guys, poor guys, are out there stringing that cable. And they string it just as tightly as they can because they're trying to save cable. They don't want to have any more expense than they had to. Well, guess what happens? In the wintertime, the cable contracts because of the linear coefficient of expansion. Temperature goes up, things expand. When the temperature drops, it contracts. If you didn't allow for some sag in the summertime, you're going to break the power pole. It's that strong of a force. Okay? So you've got to have that catenary, that especially in the summertime. If you can, sometimes go take a picture of some two power poles with a line in between it. Take it the coldest day of the year, take it from the same position the warmest day of the year, and you'll see that it sags a lot more in the summer than it does in the winter. Okay? That's sort of a side point. The reason is there's always weight pulling down. Now, of course, a suspension bridge, you got the whole bridge pulling down on it, so that really has a large catenary there. All right. Now, what lies ahead throughout the text, you'll see three different types of approaches to or analysis of differential equations. The analytical approach, the qualitative analysis, and numerical analysis. Okay? Analytical, we're going to solve it using whatever we can. Qualitative, you just sort of get the warm and fuzzy of what's going on. Numerical, you actually set up a finite difference or finite a model and let the computer do it. All right. Boy. Let's look at remarks just quickly. More precise terms, the dynamical system consists of a set of time-dependent variables called state variables. Oh, we are out of time, aren't we? Sorry about that. But we just finished. The state of the system is basically what you're looking for. Response of the system is if you have a specific initial value, how does that make your system change? So homework exercises here. Population, do 1 or 3 or both. Newton's law of cooling, do number 5, spread of disease or technology. Okay, what they mean by that, you could have spread of a disease, a virus and a disease like flu. That could also work for computer viruses. They follow the same model. So that's number 7. Mixtures, 9 or 11. Draining a tank, number 13. Series circuits, 15. Falling bodies, air resistance, 17. And Newton's second law, Archimedes' principle, which we didn't really go into in class, but that's an even number problem anyway, so you don't have to do it. By the way, Archimedes is another potential paper topic, or his principle is another one. Several things you could do there. Newton's second law and Hooke's law, we didn't go over one of those in class, but there's number 19, I think. And by the way, Hooke is another person you can write on, or how did he develop Hooke's law. By the way, Robert Hooke and Isaac Newton sometimes got along sort of, but most of the time fought with each other, so they weren't very good buddies either. Newton's second law of variable mass, that would be number 21. Newton's second law of universal gravitation, that would be 23. Other mathematical models, 25, 27, 29. You can look at several of those. There's not a lot to do in those, but There they are. Okay. I didn't make out, I made out the test, but I didn't run copies. If you want me to, I'll make copies now so you'll have it if you want to start working on it. Okay. Huh? You can wait. Okay. What I'm going to do then is end this.